In the mid-20th century, as radio astronomy matured and telescopes capable of detecting electromagnetic radiation far below the frequency of visible light came online, astronomers began discovering structures associated with galaxies that had no counterpart in optical observations. They found enormous lobes of radio-emitting plasma extending outward from certain galaxies, sometimes symmetrically, sometimes slightly offset, stretching into intergalactic space far beyond the visible boundary of the galaxy's stars. These lobes were not made of stars. They were not gas clouds in the conventional sense. They were vast reservoirs of magnetized plasma, inflated by relativistic jets of material fired from the vicinity of the galaxy's central supermassive black hole, heated to such extreme energies that they emitted synchrotron radiation detectable by radio telescopes. The mechanism behind these structures deserves a closer look, because it is one of the most violent and physically extreme processes in the entire cosmos. At the center of certain galaxies, the supermassive black hole is actively accreting material, pulling in gas and dust from its surroundings, and forming a rapidly spinning accretion disk. This disk is not a calm, orderly structure. It is a superheated maelstrom of plasma, spiraling inward at velocities approaching the speed of light, compressed by gravitational forces so intense that the inner regions of the disk and its surrounding corona reach temperatures of hundreds of millions of degrees. Friction within the disk converts gravitational potential energy into radiation, and at the peak of its activity, the accretion disk around a supermassive black hole can outshine the entire galaxy that hosts it. But not all of the infalling material reaches the black hole's event horizon. A fraction of it, channeled by powerful magnetic fields threading the accretion disk and the spinning black hole's ergosphere, gets launched outward along the black hole's rotational axis in two tightly collimated beams called relativistic jets. These jets travel at velocities approaching the speed of light, sometimes exceeding 99% of it. They are among the most energetic phenomena in the universe, carrying the power output of trillions of suns in two narrow beams that punch through the galaxy's interstellar medium and continue outward into intergalactic space. As the jets interact with the surrounding gas, they slow down, spread out, and inflate enormous lobes of magnetized plasma. These lobes grow over millions of years, fed continuously by the jets, expanding outward until the pressure of the intergalactic medium balances the energy being pumped into them. The electrons in the lobes spiral around the magnetic field lines at relativistic speeds, emitting synchrotron radiation that peaks at radio wavelengths. This radiation is how astronomers detect the lobes, which are otherwise invisible to optical telescopes. The lobes glow only in radio light, ghostly structures spanning distances that dwarf the visible galaxy at their center. Most radio galaxies produce lobes that extend a few 100,000 light-years from the central galaxy. Impressive, but comparable in scale to the galaxy's own stellar body. The lobes sit like two bubbles flanking the galaxy, visible only in radio wavelengths, invisible to optical telescopes. Even the Milky Way has its own pair of modest radio lobes, detected in recent years, extending above and below the galactic plane. These structures are a normal part of galactic astrophysics, a consequence of black hole activity that most large galaxies experience at some point in their evolution. But there is a subclass of radio galaxies that defies this modest scaling. Astronomers call them giant radio galaxies, and their defining characteristic is that their radio lobes extend to truly extraordinary distances, reaching lengths measured not in hundreds of thousands of light-years but in millions. Some span several megaparsecs, a unit of distance equal to roughly 3.26 million light-years. These are structures so vast that they do not merely extend beyond their host galaxy. They extend beyond the galaxy's local environment, beyond the scale of galaxy groups, into the spaces between cosmic web filaments. They are, by some metrics, the largest coherent structures produced by a single galactic source in the observable universe. Giant radio galaxies have been known for decades. By the early 2020s, hundreds of them had been catalogued, most discovered through radio surveys that mapped the sky at low frequencies where these extended, diffuse structures are easiest to detect. But the discoveries that shattered the public conversation about the largest galaxy came in rapid succession starting in 2022, and they changed the framing of this question permanently. In February of 2022, a team of astronomers led by Martijn Ooi at the Leiden Observatory in the Netherlands published a paper announcing the discovery of a giant radio galaxy they named Alcyoneus, after one of the giants of Greek mythology. The galaxy was identified in data from the Low Frequency Array, or LOFAR, a network of roughly 20,000 individual radio antennas distributed across 52 stations in Europe. LOFAR operates at frequencies far below what optical telescopes detect, and its sensitivity to faint, diffuse radio emission makes it ideally suited for detecting the extended lobes of giant radio galaxies. What Oe and his colleagues found was remarkable. Alcyoneus possessed a radio structure spanning approximately 5 megaparsecs in projected length, which translates to roughly 16 million light-years from one lobe edge to the other. To put that in context, the Milky Way is approximately 100,000 to 200,000 light-years across. Alcyoneus's radio structure was roughly 100 times the diameter of the Milky Way. Laid end to end, you would need 100 Milky Way galaxies to match the span of this single radio structure. At the time of its discovery, it was the largest known structure of galactic origin ever detected. The media response was immediate and, in many cases, misleading. Headlines declared Alcyoneus the largest galaxy in the universe. Social media amplified the claim. The name Alcyoneus began appearing on lists of cosmic records alongside IC 1101, often presented as though the two objects were competing in the same category. But this framing obscured a critical distinction that matters enormously for understanding what largest actually means. Alcyoneus's host galaxy, the actual stellar body at the center of the radio structure, is not exceptional. Its stellar mass is estimated at roughly 240 billion solar masses, which is only a few times that of the Milky Way and far smaller than IC 1101's estimated 100 trillion stars. Its central supermassive black hole weighs approximately 390 million solar masses, a respectable but entirely ordinary mass for an elliptical galaxy, and roughly 100 to 250 times less massive than the black hole in IC 1101. The galaxy itself does not host a quasar. Its star formation rate is negligible, at roughly 1/60th of a solar mass per year. By every measure of the visible stellar body, the host galaxy of Alcyoneus is unremarkable. It is an ordinary elliptical galaxy embedded in a filament of the cosmic web, indistinguishable from thousands of similar objects scattered throughout the observable universe. What makes Alcyoneus extraordinary is not its galaxy, it is its jets. It is the two enormous lobes of magnetized plasma extending millions of light-years in opposite directions from the central black hole, inflated over millions of years by relativistic outflows that have been pumping energy into intergalactic space. These lobes are not made of stars. They contain no planets, no solid matter, no structure that would be recognizable as galactic in the traditional sense. They are tenuous, diffuse clouds of plasma so thin that their internal pressures rank among the lowest ever measured in any astrophysical structure, approximately 5 times 10 to the -16th pascals. They glow only in radio wavelengths, invisible to any optical telescope ever built, and this is the detail that makes Alcyoneus so conceptually disorienting. The galaxy at the center is ordinary, unremarkable, a galaxy you would walk past in a catalogue without a second glance. Its stellar mass is half that of the Milky Way. Its black hole is 100 times less massive than the largest known. Its radioluminosity sits at roughly the 45th percentile of all known giant radio galaxies, meaning more than half of them are actually brighter. The mismatch between cause and effect is almost absurd. Strip away the radio lobes and you are left with a galaxy that no survey would flag as unusual. Restore them, and you are looking at a structure 100 times wider than the Milky Way. The engine is modest. The output is colossal. It is as if a garden hose somehow produced a river. This disconnect between the host galaxy and the scale of the radio structure is one of the deepest puzzles in modern extragalactic astronomy. If the jets were driven by an exceptionally powerful black hole, the enormous size would make intuitive sense. More power, more reach. But Alcyoneus has a modest black hole by the standards of active galaxies. If the jets were unusually energetic, that would explain the extent. But Alcyoneus's jet luminosity is ordinary. The most plausible explanation, and the one proposed by the Discovery team, is that the growth of the radio lobes was primarily determined not by the power of the central engine, but by the density of the surrounding environment. Alcyoneus resides in a filament of the cosmic web where the intergalactic medium may be less dense than average. With less resistance pushing back against the expanding lobes, The same modest jet power that would produce ordinary-sized lobes in a denser environment instead produced a structure spanning 16 million light-years in the relative vacuum of a sparse cosmic filament. This is the core of the ambiguity. When the media called Alcyoneus the largest galaxy, they were including the radiolobes in the measurement. But radiolobes are not typically considered part of a galaxy's size in standard astronomical usage. They are ejecta, material expelled from the galaxy rather than material contained within it. The Wikipedia article on Alcyoneus itself notes that various media outlets described it as the largest galaxy known, but adds that this is misleading because radio ejecta are not often taken into consideration in determining galaxy sizes. The distinction is not pedantic. It reflects a genuine scientific question about what a galaxy is. Is a galaxy defined by its stars, by the gravitational extent of its dark matter halo, by the furthest reach of any structure physically connected to its central engine? The answer determines whether Alcyoneus is the largest galaxy ever found, or merely the galaxy with the largest radio ejecta ever found. And those are meaningfully different claims. But even as astronomers were processing the implications of Alcyoneus, the record was already being broken again. In September of 2024, a paper published in the journal Nature by a team again led by Martijn O announced the discovery of an even larger giant radio galaxy. This one was named Porphyrion, after another giant of Greek mythology, and its scale made Alcyoneus look modest by comparison. Porphyrion's radio jets span approximately 7 megaparsecs, or roughly 23 million light-years, from end to end. That is 140 times the diameter of the Milky Way. If you could somehow see Porphyrion's full extent with the naked eye, the two lobes would dominate a colossal swath of the sky, dwarfing any individual galaxy by an almost absurd margin. The host galaxy lies 7.5 billion light-years from Earth, meaning the jets existed when the universe was only 6.3 billion years old, less than half its current age. Despite its extreme youth in cosmic terms, the central black hole generated jets with a combined power output equivalent to the energy of trillions of suns, punching plasma into intergalactic space at nearly the speed of light and inflating lobes that stretched across a volume of space comparable in scale to the gaps between filaments of the cosmic web. Porphyrion's discovery carried implications that went far beyond the question of galactic size records. The research team calculated that the jets span roughly 2/3 the radius of a typical cosmic void at that epoch of universal history. This means a single galaxy's outflows were reaching scales that interact not just with the galaxy's local environment, but with the large-scale structure of the universe itself. The jets were threading through the cosmic web, potentially magnetizing the intergalactic medium, heating the gas between filaments, and influencing the formation and evolution of other galaxies located millions of light-years from the source. Oe and his colleagues wrote that their findings suggest every place in the universe may have been affected by black hole activity at some point in cosmic time. This idea, that black hole jets might be responsible for magnetizing the cosmos on the largest scales, represents a significant shift in astrophysical thinking. For years, the origin of magnetic fields in the intergalactic medium was a nagging puzzle. Observations confirmed that the gas between galaxies is permeated by weak but measurable magnetic fields, but the mechanism that produced them was debated. One leading hypothesis, called the Biermann battery effect, proposed that magnetic fields arise naturally from the differential motion of electrons and ions under gravitational forces. This mechanism works, but it produces extremely weak seed fields that need amplification by other processes to match observed strengths. Giant radio galaxy jets offer an alternative and potentially more powerful explanation. If jets spanning tens of millions of light-years routinely inject magnetized plasma into the intergalactic medium, they could be the primary source of cosmic magnetism on the largest scales. Porphyrion's discovery strengthened this hypothesis by demonstrating that jet structures can reach sizes comparable to the cosmic web itself, placing magnetized plasma exactly where it would need to be to explain the observed intergalactic fields. And even Porphyrion's record did not last. By late 2024, another radio galaxy designated TXS-003, 3+252, was identified with an estimated radio structure spanning approximately 8 megaparsecs, or roughly 26 million light-years. The records are falling faster than the community can absorb them, driven by the unprecedented sensitivity of LOFAR and the growing recognition that giant radio galaxies are far more common than previously believed. A citizen science effort associated with the LOFAR surveys has already identified more than 10,000 jet pairs spanning roughly 3 million light-years or more. These are not rare curiosities. They are a population, a class of objects that the universe produces routinely, and their typical scales dwarf anything measured in visible starlight. Now pause and consider what this means for the question at the heart of this discussion. What is the largest galaxy we have ever found? The answer depends entirely on how you define galaxy. If you define a galaxy by its visible stellar body, the extent of its stars and the light they produce, then IC 1101 remains one of the strongest candidates. Its isophotral diameter of 400,000 to 550,000 light-years, combined with a diffuse stellar halo extending to roughly 4 million light-years, places it at or near the top of every observed distribution of visible galactic size. No other galaxy has been reliably measured with a brighter, more extended stellar body. In the category of visible galactic size, IC 1101 is the anchor, the reference point, the object that defines the extreme end of the scale. But if you define a galaxy by the total extent of any coherent physical structure connected to its central engine, including radio lobes inflated by relativistic jets, then the record belongs to objects like Porphyrion and its successors. Their physical extents of 23 to 26 million light-years exceed the halo of IC 1101 by factors of roughly 6 to 7. They reach distances that place them in a different category entirely, structures that span not just galactic scales but cosmological ones. The tension between these two definitions is not a flaw in astronomy, it is a reflection of a genuine physical reality. Galaxies are not simple objects. They are multi-layered systems with stellar bodies, dark matter halos, gas reservoirs, magnetic fields, and in some cases, relativistic outflows that extend far beyond anything the stars alone could reach. Choosing where to draw the boundary is not arbitrary, but it is a decision, and different decisions produce different answers. An astronomer studying stellar populations might define galaxy size by the extent of the stars and conclude that IC 1101 is the largest. A radio astronomer studying jet physics might define galaxy size by the extent of the radio structure and conclude that Porphyrion holds the record. Both are correct within their frameworks. Neither is wrong. The universe simply does not provide a single, unambiguous answer. But here is what matters more than the record itself. The existence of these giant radio structures tells us something deeply uncomfortable about the range of scales the universe can produce from a single galactic source. When Alcyonius was discovered, astronomers were surprised not by the existence of giant radio galaxies, which had been known for decades, but by the fact that the host galaxy was so ordinary. Its stellar mass was average, its black hole was average, its jet luminosity was average. Nothing about the central engine was exceptional, yet it produced a radio structure spanning 16 million light-years. The implication was that giant radio galaxy growth might not require unusual central engines. It might require only the right environment, a low-density region of the cosmic web where the intergalactic medium offers minimal resistance to the expanding lobes, allowing them to grow to extraordinary sizes without being confined by external pressure. Porphyrion complicated this picture further because its host galaxy is more massive, roughly 10 times the mass of the Milky Way, and its black hole operates in a different mode, a radiative mode, rather than the jet mode typical of most giant radio galaxies. This was unexpected, because radiative mode black holes were not previously known to produce jets of this scale. The discovery implied that the conditions for giant jet growth might be more varied and more common than astronomers had assumed. If both ordinary and massive host galaxies can produce jets spanning tens of millions of light-years, and if the primary limiting factor is the density of the surrounding intergalactic medium rather than the power of the central engine, then the universe may contain far more of these structures than current surveys have detected. LOFAR has so far surveyed only about 15% of the sky. The population of giant radio galaxies identified already numbers in the thousands, and the survey is nowhere near complete. OE himself has stated that astronomers may be looking at the tip of the iceberg. The true population of structures spanning millions of light-years could be vastly larger than current catalogues suggest. This realization does not diminish IC 1101. If anything, it contextualizes it more precisely. IC 1101 represents the extreme of one kind of galactic scale, the visible stellar kind. Its stellar body, its halo, its core, its black hole, all push the limits of what the universe can build through gravitational assembly and galactic mergers. It is the end product of billions of years of gravitational assembly at the center of a massive galaxy cluster, and in terms of the sheer mass and extent of assembled starlight, it remains one of the most extreme objects ever observed. But the giant radio galaxies represent the extreme of a different kind of galactic scale, the kind measured not in stars but in energy, in magnetic fields, in the reach of relativistic plasma, driven outward by the most powerful engines in the cosmos. These structures do not compete with IC 1101 for the same title. They occupy a different axis of extremity entirely. And the fact that both kinds of extreme exist, that the universe can build galaxies as visually massive as IC 1101 and simultaneously produce single-source structures as physically extended as Porphyrion, is what makes this story genuinely unsettling rather than merely impressive. Because the real question is not which galaxy holds the record. The real question is what it means that the universe can produce structures at these scales at all. A galaxy whose stars span 500,000 light-years and whose halo reaches 4 million. A single black hole's outflow that spans 23 million light-years. A population of giant jets numbering in the tens of thousands, most of them still undetected. The scales involved are not just large, they are large enough to interact with the cosmic web itself, the largest organizational structure in the universe. When a single galaxy's jets can stretch across 2/3 the radius of a cosmic void, the old image of a galaxy as an island surrounded by empty space stops working. These objects are not contained by their local environment. Their outputs leak across distances that compete with the spacing of the cosmic web's own filaments, depositing magnetized plasma into regions no star from the host galaxy will ever reach. A single galactic engine is operating on a canvas that was supposed to belong to the universe alone. This is where the emotional weight of the story shifts. We began by establishing that a single ordinary galaxy is already incomprehensibly large. Then we showed that IC 1101 pushes visible galactic size to a point where familiar references like the Milky Way and Andromeda stop functioning as meaningful comparisons. Now we have seen that the concept of the largest galaxy itself resists clean definition, because the universe produces galactic structures across multiple axes of scale that do not collapse into a single ranking, and the structures at the top of each axis are so extreme that they begin to blur the categories astronomers use to organize the cosmos. A galaxy is supposed to be a bounded object, a collection of stars and gas and dark matter held together by gravity, distinct from its surroundings, definable, measurable. But when a galaxy's radio lobes extend 23 million light-years into intergalactic space, is the structure still a galaxy? When a galaxy's stellar halo merges imperceptibly into the intracluster light of its parent cluster, where does the galaxy end and the cluster begin? When a galaxy's jets magnetize the cosmic web across scales rivaling the distances between filaments, is the galaxy's influence truly local? These are not rhetorical questions. They are active areas of research. And the answers, when they come, will likely reveal that the boundaries we draw around galaxies are human constructs imposed on a cosmos that does not recognize them. The universe builds structures continuously, from stellar scales to galactic scales to cluster scales to cosmic web scales, and the transitions between them are not sharp, they are gradients. Zones of diminishing influence that fade rather than end. A galaxy is not a thing with an edge, it is a concentration of matter and energy at the center of a zone of influence that extends, in principle, forever. IC 1101 and Porphyrion are both expressions of this truth. One represents the extreme of gravitational assembly, the largest visible pile of stars ever observed. The other represents the extreme of energetic outflow, the farthest reach of a single black hole's relativistic jets. Both are galaxies. Both defy simple measurement. Both force us to confront the uncomfortable reality that the universe's capacity for building large structures has no obvious ceiling. And it is that absence of a ceiling, that sense of unlimited upward scale, that transforms this story from a record book into something more deeply troubling. Because if the largest visible galaxy can span 4 million light-years, and the longest radio jets can reach 26 million, and the population of giant structures numbers in the tens of thousands, with most still undetected, then we are not looking at outliers. We are looking at the edge of a distribution whose full extent we have not yet mapped. Somewhere in the unobserved sky, there may be structures even larger, structures that have not yet been detected because our surveys are incomplete, because our instruments lack the sensitivity, because the universe has had billions of years to build things we have not yet imagined. The largest galaxy we have ever found may not be the largest galaxy that exists, and that possibility is where the final layer of this story begins. Let us go back to the beginning. Not the beginning of this story, but the beginning of the intuition we have been slowly dismantling across everything that came before. The intuition that says a galaxy is a knowable thing, a structure with a shape, a size, a boundary. Something you could point to on a chart and say, that is a galaxy. It starts here, it ends there, and everything outside it is something else. That intuition feels natural because it is how we experience every other object in our lives. A mountain has a base and a peak. An ocean has a shore. A city has a boundary where the buildings stop and the countryside starts. We are wired to think in terms of objects, edges, categories. And for most of human history, that wiring served us well. But the universe, at the scales we have been exploring, does not operate the way our wiring expects. And the story of the largest galaxy ever found is ultimately the story of what happens when that wiring encounters something it was never designed to process. Start with the Milky Way. 100,000 to 200,000 light-years across, 200 to 400 billion stars, a supermassive black hole weighing 4 million solar masses, a barred spiral structure with arms of gas and dust and young stars wrapping around a central bulge of older, redder stellar populations. This is home. This is the galaxy that contains every star you have ever seen, every planet humanity has ever studied, every signal we have ever sent into the void. It is so large that light requires 100,000 years to cross it. It is so massive that its gravitational influence shapes the orbits of more than 80 satellite galaxies. It contains more worlds than any human civilization could explore in 1,000,000 lifetimes. And yet, in the context of this story, the Milky Way has served only as a starting point, a baseline, the first rung on a ladder that climbs so far upward that the bottom rung eventually disappears from view. Andromeda came next. Roughly 220,000 light-years across, 1 trillion stars, a black hole weighing 100 million solar masses, larger than the Milky Way by every meaningful metric. If the Milky Way is an average house on a residential street, Andromeda is the mansion at the end of the block. Impressive, dominant, the biggest thing in the immediate neighborhood. And the two of them are falling toward each other at 250,000 miles per hour, locked in a gravitational embrace that will end in a collision roughly 4 to 5 billion years from now. When that collision occurs, both galaxies will be destroyed as independent structures and reformed into a single massive elliptical galaxy containing the combined stellar populations of both. That merged galaxy will be among the largest structures in the local cosmic neighborhood, and it will still be smaller than IC 1101 by a factor that renders the comparison almost meaningless. IC 1101, a supergiant CD galaxy at the center of the Abell 2029 galaxy cluster, 1.15 billion light-years from Earth, an isophotal diameter of 400,000 to 550,000 light-years for the visible stellar body, a diffuse stellar halo extending to a radius of roughly 2 million light-years, giving a total extent of approximately 4 million light-years, 100 trillion stars, a supermassive black hole weighing between 40 and 100 billion solar masses, the largest known galactic core ever measured, spanning roughly 14,000 light-years, carved out by the mergers of supermassive black holes during billions of years of relentless galactic consumption. A galaxy whose halo alone could swallow the distance between us and Andromeda, a single structure vast enough to replace our entire local group and still have room at the margins. That is the visible giant. That is the galaxy that held the popular title of largest in the universe for decades, and that still stands as one of the most extreme examples of assembled starlight ever observed. And for a long time, that was where the story ended. The biggest galaxy was IC 1101. The number was 4 to 6 million light-years depending on how you measured the halo, and the emotional conclusion was straightforward awe, a galaxy bigger than our local group. Case closed. But the story did not end there. It could not, because the universe was not finished revealing what it had built. Alcyoneus, discovered 2022. A giant radio galaxy whose relativistic jets inflate lobes of magnetized plasma spanning approximately 16 million light-years, roughly 100 times the diameter of the Milky Way. The host galaxy is ordinary. Its stellar mass is only modestly above the Milky Way's. Its black hole is modest by the standards of active galaxies. Nothing about the central engine is exceptional, and yet the structure it produced is 4 times larger than the full halo extent of IC 1101. Porphyrion, reported 2024. Jets spanning approximately 23 million light-years, 140 times the diameter of the Milky Way. A structure so large that it stretches across roughly 2/3 the radius of a cosmic void at the epoch when it existed, reaching scales that interact with the cosmic web itself. The host galaxy is 10 times the mass of the Milky Way, substantial but not extraordinary. The jets date to a time when the universe was only 6.3 billion years old, less than half its present age. A single black hole, less than halfway through cosmic history, producing an outflow that bridges the gap between the local galactic environment and the large-scale structure of the universe. And then TXS0033+252, identified in late 2024. Radio structure spanning approximately 26 million light-years, surpassing Porphyrion. Another record broken before the previous one had been fully absorbed by the scientific community. Another demonstration that the upper limit of galactic structural extent has not yet been found. Now lay these out in sequence and feel the ladder. The Milky Way, 100,000 to 200,000 light-years. Andromeda, 220,000 light-years. IC 1101, stellar body, 400,000 to 550,000 light-years. IC 1101, full halo, approximately 4 million light-years. Alcyoneus, full radio structure, approximately 16 million light-years. Porphyrion, full radio structure, approximately 23 million light-years. TXS0033+252, approximately 26 million light-years. Each step on that ladder does not merely increase the number, it changes the category. The jump from the Milky Way to Andromeda is a jump within the same class of objects, spiral galaxies of roughly similar structure. The jump from Andromeda to IC 1101 is a jump from a large spiral to a supergiant elliptical, a fundamentally different type of galaxy built through fundamentally different processes. The jump from IC 1101's stellar body to its halo is a jump from the galaxy's bright interior to its fading gravitational periphery, a zone where the boundary between galaxy and cluster becomes ambiguous. And the jump from IC 1101's halo to the radio structures of Alcyoneus and Porphyrion is a jump from assembled starlight to relativistic plasma, from gravitational architecture to energetic outflow, from the galaxy as a collection of stars to the galaxy as a source of influence that extends across cosmological distances. At each step, the previous reference point shrinks. The Milky Way, which felt impossibly vast at the start, becomes a rounding error by the time you reach IC 1101. IC 1101, which seemed like the ultimate expression of galactic scale, becomes a dot at the center of Porphyrion's radio structure. The comparisons that once made you feel the size, the ones that said IC 1101 could swallow the local group, or that Porphyrion equals 140 Milky Ways laid end to end, stop producing the emotional response they were designed to create. The numbers are too large, the gaps between the rungs are too wide, the ladder has climbed past the altitude where human intuition can breathe. This is what I mean when I say scale itself fails. It is not that the numbers become meaningless in a mathematical sense. They remain precise, measurable, scientifically valid. It is that they become meaningless in a human sense. The emotional apparatus we use to process size, the instinct that makes a mountain feel large and a continent feel larger, breaks down when confronted with structures that span millions or tens of millions of light-years. We lose the ability to feel the difference between 16 million light-years and 23 million light-years because both numbers are already so far beyond anything we can viscerally imagine that adding 7 million more makes no experiential difference. The ladder keeps climbing, but at some point the climber goes numb, and that numbness is itself the point. Because the terrifying truth about the largest galaxy we have ever found is not a specific number, It is not 4 million light-years or 16 million or 23 million. The terrifying truth is the shape of the distribution. It is the fact that every time astronomers survey a new patch of sky with better instruments, they find structures larger than the ones they knew about before. It is the fact that LOFAR has surveyed only 15% of the sky and has already identified more than 10,000 giant jet pairs spanning millions of light-years. It is the fact that the records keep falling, not because we are getting close to the maximum, but because we keep discovering that the maximum is further away than we thought. There is no indication that we have found the largest galactic structure the universe has produced. There is no theoretical ceiling that says radio jets cannot extend beyond 30 million light-years, or 40, or 50. The limiting factor appears to be the density of the intergalactic medium, which varies from region to region across the cosmic web. In denser environments, jets are confined and cannot grow as large. In sparser environments, in the voids between filaments where the intergalactic medium is thinnest, jets can expand with minimal resistance. If there exists somewhere in the unobserved universe, a supermassive black hole embedded in a galaxy sitting in an unusually sparse region of the cosmic web, with just the right accretion rate and just the right jet orientation, its radio structure could potentially extend to scales we have not yet observed. The records that Alcyonius and Porphyrion set may be records only of our current observational capability, not of the universe's capacity for construction. And our observational capability is about to increase dramatically. LOFAR, the instrument responsible for nearly every giant radio galaxy breakthrough of the past 5 years, has mapped only 15% of the northern sky. The full survey, when complete, will cover the entire northern hemisphere at sensitivities that dwarf earlier radio surveys. Every previous expansion of LOFAR coverage has revealed new giant structures, new record holders, new populations of objects that were invisible to earlier instruments. There is no reason to expect this trend to stop. The remaining 85% of the northern sky almost certainly contains giant radio galaxies that surpass everything currently known. But LOFAR itself will eventually be surpassed. The Square Kilometre Array, or SKA, is an international radio telescope project currently under construction across sites in South Africa and Australia. When completed, it will be the most sensitive radio telescope ever built, with a total collecting area of approximately 1 square kilometre and a sensitivity that exceeds LOFAR by an order of magnitude. The SKA will survey the entire sky, both hemispheres at frequencies and resolutions that make current instruments look primitive. It will detect radio lobes so faint and so extended that they are invisible to every existing telescope. If giant radio galaxies are as common as LOFAR's partial surveys suggest, the SKA will discover them in the hundreds of thousands. It will map the full population of giant jet structures across the observable universe, revealing for the first time the true statistical distribution of the largest galactic structures in existence. What that distribution looks like is one of the most consequential unknowns in extragalactic astronomy. If it has a sharp cutoff, a maximum scale beyond which jets simply cannot grow, then the current records are close to the physical limit. If it has a long tail, extending to sizes significantly larger than anything yet observed, then the universe contains structures of galactic origin that we have not yet imagined. The data needed to distinguish between these possibilities does not yet exist. It is waiting in the unobserved sky, encoded in radio photons that have been travelling through intergalactic space for billions of years, carrying information about structures so large that the galaxies at their centres are invisible specks within their own creations. This is what separates this story from a simple exercise in big numbers. It is not just that the largest galaxies are large, it is that the concept of largest resists closure. Every answer we give comes with a caveat. IC 1101 is the largest visible galaxy, but the boundaries of its halo are ambiguous. Porphyrion has the largest measured radio structure, but its record lasted only months before being surpassed. The largest galaxy ever found is a moving target, and the direction it moves is always upward. And beyond the question of individual records, there is a deeper and more unsettling realization. The existence of these structures changes the way we must think about what a galaxy is, and what role it plays in the universe. For most of the history of astronomy, galaxies were treated as discrete objects, islands of stars separated by vast, empty spaces. The space between galaxies was considered largely inert, a vacuum populated only by sparse intergalactic gas and the invisible scaffolding of dark matter. Galaxies were the actors. The space between them was the stage, but giant radio galaxies dissolve this distinction. When a single galaxy's jets span 23 million light-years, threading through the cosmic web, magnetizing the intergalactic medium, heating gas in neighboring filaments, the galaxy is no longer confined to its own island. Its influence has leaked out, contaminated the space between structures, blurred the boundary between actor and stage. Oe and his colleagues wrote that their findings suggest supermassive black holes do not only hold sway over the galaxy, but also over the cosmic web that surrounds them. This is not a minor addendum to our understanding of galactic physics. It is a fundamental reframing. Galaxies are not just objects within the cosmic web. Some of them are architects of the cosmic web, shaping its properties across scales that rival the web's own organizational structure. Consider what this means for the Milky Way. Our galaxy is a normal barred spiral with a modestly sized supermassive black hole. Its radio lobes are small by the standards of giant radio galaxies. Its influence extends, in stellar terms, only a few 100,000 light-years. In the context of the cosmic web, the Milky Way is a moat. A single node in a filament, gravitationally bound to a small group of neighbours, falling slowly toward the Virgo cluster along with the rest of the Laniakea supercluster. Our galaxy's influence on the large-scale structure of the universe is negligible, but the Milky Way's insignificance at these scales goes deeper than mere size. It is structural. At the scale of Porphyrion's jets, our galaxy is not merely small, it is invisible. If you could somehow view the full extent of Porphyrion's radio structure from a distance sufficient to see both lobes at once, the Milky Way, placed anywhere within that structure, would be undetectable. Not faint, not small, undetectable. A galaxy containing 400 billion stars, a supermassive black hole, spiral arms spanning 100,000 light-years, and it would register as nothing, a fluctuation below the noise floor. The structure we call home, the galaxy we have spent centuries studying, the cosmic address we use to locate ourselves in the universe, would be lost in the plasma like a single bacterium floating in an ocean. Not marginalized, not diminished, erased. This is not a poetic exaggeration. It is a direct consequence of the numbers. Porphyrion spans 23 million light-years. The Milky Way spans 200,000. The ratio is roughly 115 to 1. If Porphyrion's radio structure were scaled to the length of a football field, the Milky Way would span barely a single yard of the total distance. Our entire galaxy, with all its stars, all its planets, all its civilizations that might exist, reduced to a single stride on a playing surface, you would need a full minute to walk from end to end. That is the scale we are dealing with. That is what the universe has demonstrated it can build from a single galactic source. And here is the part that makes this personal, in a way that abstract numbers never can. Every measurement humanity has ever made of the cosmos has been made from inside the Milky Way. Every telescope, every space probe, every photon we have ever collected has arrived at instruments located within our galaxy. Our entire understanding of the universe is built on observations made from a platform that, at the scales being considered, barely qualifies as a location. We are not observing the cosmos from a meaningful vantage point. We are observing it from a pixel. A single, unremarkable pixel in a structure so vast that the structure itself is unremarkable compared to what the universe can build. Every astronomy textbook, every map of the cosmic web, every diagram of the observable universe, all of them place the Milky Way at the center because that is where the observer is located. But the centrality is observational, not physical. There is nothing special about our position. There is nothing special about our galaxy. There is nothing special about the filament we inhabit or the supercluster we belong to. We are an average galaxy in an average location, and the only reason the universe appears to radiate outward from us is that light takes time to travel, creating a spherical observational horizon centered on wherever the observer happens to stand. An observer in IC 1101 would see a different observable universe, centered on a different point, containing different galaxies at different distances. An observer in Porphyrion's host galaxy would see yet another. Every location in the cosmos is the center of its own observational sphere, and none of them is privileged. But IC 1101, sitting at the center of Abell 2029, shapes the thermal properties of its entire cluster. Its black hole's past activity influenced gas dynamics across millions of light-years. Its gravitational dominance accreted material from the cosmic web along the axis, connecting its cluster to the neighbouring Abell 2033. It is not merely embedded in the cosmic web, it has consumed enough of its local web to become the dominant feature of its own cosmic neighbourhood. And Porphyrion, with its jets reaching 2/3 the radius of a cosmic void, does not merely sit in the web, it reaches across the web. Its outflows interact with the intergalactic medium on scales that rival the voids themselves. A single galaxy's black hole, pumping energy into space at the rate of trillions of suns, sculpting the magnetic field of the cosmos across distances that dwarf everything we have ever called large. This is the emotional core of the story. Not the numbers, not the records, not the debate over which galaxy is technically the biggest. The emotional core is the realization that galaxies can become so large, and their influence can extend so far, that they stop being things inside the universe and start being things that shape the universe. At the extreme end of the scale distribution, the distinction between a galaxy and a cosmic structure begins to dissolve. The galaxy does not merely occupy a position in the cosmic web, it modifies the web. It reaches across the voids, it touches other filaments, it injects energy, magnetism, and heat into regions that were supposed to be empty and inert. The Milky Way is enormous, Andromeda is larger, IC 1101 is vastly larger still, and the giant radio galaxies extend to scales that make even IC 1101 feel contained and local. Each comparison erases the emotional weight of the previous one. Each new rung on the ladder diminishes everything below it. And the ladder, as far as we can tell, has no top. There is a specific kind of cognitive vertigo that arrives when you follow this ladder all the way up. It is not the same as the awe you feel looking at a photograph of a galaxy. That awe is comfortable. It is the vertigo of realizing that the cosmos has no obligation to remain within the boundaries of your imagination. You can build a mental model of the Milky Way. You can hold it in your head as an image, a concept, a thing with a shape and a size. You can do the same for Andromeda, with effort. You can even do it for IC 1101, if you anchor it to the comparison with the local group. But you cannot hold Porphyrion. You cannot visualize 23 million light-years of relativistic plasma extending from a single point source into the void between cosmic web filaments. The image does not fit. The frame of reference you need does not exist in human experience. The structure is real, measured, confirmed, but it exists beyond the threshold of what our evolved cognitive architecture can render as a picture. And that failure of visualization is not a weakness of science communication, it is the point. The universe at these scales is not supposed to make intuitive sense. It was not built for human comprehension. It was built by gravity, by thermodynamics, by the relentless physics of accretion and ejection, operating over billions of years without any awareness that a species on a small planet in a minor spiral arm would one day try to picture what it had done. The structures exist whether or not we can imagine them. The lobes expand whether or not we can feel their size. The galaxies grow whether or not we have words adequate to describe them. The terrifying size of the largest galaxy we have ever found is not a single number. It is a spectrum. At one end sits IC 1101, the anchor, the visible giant, the most extreme expression of assembled starlight ever observed. A galaxy whose stellar body and halo span millions of light-years, and whose black hole ranks among the most massive objects in the cosmos. At the other end sit the giant radio galaxies, Alcyoneus and Porphyrion, and the unnamed structures still waiting to be detected in the unobserved sky, whose physical extents reach tens of millions of light-years, and whose influence extends to the architecture of the cosmic web itself. Between these two endpoints lies the ambiguity of definition, the honest acknowledgement that largest depends on what you measure, and that the universe refuses to provide a single, clean answer. But the ambiguity does not weaken the story, it deepens it. Because the truly terrifying realization is not that one specific galaxy is big. It is that the universe can produce galactic structures so vast, across so many different axes of measurement, that even the galaxies we already treat as immense, the Milky Way and Andromeda and Messier 87 and every other galaxy we have ever photographed and studied and named, begin to look local, begin to look small, begin to look like details in a picture whose full extent we have not yet seen and may never fully see. The Milky Way is not a large galaxy. It is a speck orbiting inside a supercluster that is itself a minor feature of the cosmic web. Andromeda is not a giant. It is one island among 2 trillion in an observable universe that may represent less than 1% of total cosmic volume. And even C1101, the most visually extreme galaxy ever measured, sits at the center of one cluster in one filament of a web that stretches across 93 billion light-years of observable space and likely extends far beyond. The largest galaxy we have ever found is not a settled answer. It is a question that keeps expanding, just like the structures it describes. The records will keep falling. The instruments will keep improving. The 85% of the sky that LOFAR has not yet surveyed will yield structures that surpass everything in current catalogues. The square-kilometre array will peer deeper into the radio universe than any instrument before it, mapping populations of giant jets that are currently invisible. And each new discovery will push the upper end of the distribution further outward, further from human intuition, further from any framework that allows us to feel the scale rather than merely calculate it.